Hello, today we're going to talk about wave-particle duality and what it means to the double slit experiment. We will also briefly discuss Huygens Principle as it relates to this. Here's a disclaimer. The material is based on sound scientific principles. The opinions expressed here are mine, based on the observations we are going to make. This presentation has not been peer-reviewed or accepted by any journal. The information in this presentation is general in nature and not intended as professional guidance, nor will it assist you in passing any exams. You are encouraged to confirm any information obtained from this presentation with other sources, and this material is copyrighted. This presentation will address the following concepts. We will describe the problem to be addressed. We will first describe the original double slit experiment. We will then explain how an aperture antenna works and what current bunching is. Next, we will talk about electrostatic repulsion and moving charges. Finally, we will put this all together to explain how a single particle can produce an interference pattern. The idea for this presentation was inspired by a video on the double slit experiment. See the link below. In it, a charged particle passed through one of the slits and produced an interference pattern. This begs the question, how can a single particle produce an interference pattern? Let's start with some background on the double slit experiment. In the early 19th century, there was much debate as to whether light was a particle or a wave. Thomas Young built the double slit experiment. The source was a candle placed behind a hole in a mask. This illuminated another mask having two slits as shown. An interference pattern was produced, and the wave nature of light was inferred. We will take a non-traditional look at this experiment using classical electromagnetics. Consider a slit on a conducting surface. The slit can be thought of as an aperture antenna. An aperture antenna can radiate signals. Under simplifying conditions, an aperture antenna behaves much like an electric dipole antenna, except that the equations for the electric and magnetic fields are switched. In the illustration below, the dots represent free electrons embedded in a conducting sheet. Let's say that an electromagnetic pulse illuminates this sheet. This induces a current pulse, which moves to the right across the surface of the sheet. If an aperture is present, it partially blocks the current flow. The current bunches up along the edge of the aperture. Some of the energy is reflected, and some moves across the aperture because of electrostatic repulsion. The green arrows represent the induced electric field whenever current bunches up along the edge of the aperture. When the current pulse strikes the aperture, electrons on the opposite side are pushed away from the edge and continue moving. While the electrons are pushed up against the aperture, there is a difference in electric potential, which induces an electric field. This field radiates in and out of the plane of the sheet. Current can be induced on the surface by radio or light. In the experiment, there are a pair of slits, and an interference pattern is produced. Huygens' principle states that every point on a wave is itself a source of spherical waves. Some of these spherical waves can form a new wave. The previous slide agrees with this concept. The electrons in the conducting sheet interact with the electromagnetic field. At each point, they are influenced by the field, causing them to move. This movement causes a re-radiation of fields from each electron. Where there is matter, each point can produce a new spherical wavefront. We know that like charges repel each other, and opposite charges attract. Electrons repel other electrons. In this animation, we see a charged particle moving toward a conducting sheet. So as the particle approaches the sheet, electrostatic repulsion pushes the electrons in the sheet away from the point of impact. Conversely, if the charged particle moves away from the sheet, the displaced electrons rush inward. Similarly, if the charged particle were to pass through a hole in the sheet, we would see a similar behavior where the electrons move radially outward, then rush inward. The speed of the moving particle affects the velocity of the other electrons. Here we have shown a slow-moving particle where no oscillations, overshoots, or undershoots are observed. Now let's put it all together. In the top figure, we have an electron in red moving toward the surface. The electron can strike the surface anywhere or even pass through one of the slits. The charge repels the other surface charges, pushing them outward, then back inward as the charge is either absorbed or passes through one of the slits. The induced current wave induces fields across both apertures, which then radiate outward. Where the particle strikes will affect the phase between the slits, steering the interference pattern up or down slightly. Electron velocity and slit spacing might also be a factor. The bottom figure is a representation with current bunching that bounces between the slits in a semi-resonant manner while dissipating. We've shown how a single particle can produce an interference pattern. A single particle does not have much energy, so measurement of the interference pattern in the presence of noise can be very difficult. It may be necessary to repeat the experiment to pull an average signal up out of the noise. A string of particles, all having the same velocity and point of impact, would improve the signal to noise so that the pattern becomes measurable. It is important that the point of impact be the same for all particles, since it will affect the phase between slits. If not controlled, the pattern will appear blurred, as it will shift up and down slightly from pulse to pulse. It is possible that this will work with light if we can assume that the photons are large enough to impact the mask, and it is possible for them to induce eddy currents around the point of impact. We have shown a single particle can cause a pair of slits to produce an interference pattern. This gives the appearance that the particle was really a wave that passed through both slits, or that there was some sort of quantum superposition. We have shown that a charged particle can induce currents onto the sheet through electrostatic repulsion of the free electrons on a conducting surface. These charges then cause current bunching around the slits, which radiate through the slits because they are aperture antennas and produce an interference pattern. We've also given a practical explanation of Huygens' principle. If you found this presentation interesting and/or informative, please like and subscribe. Thank you.